Hello, everyone. I'm glad to participate in this conference. I'm Fansheng from Jilin University, and my supervisor is Professor Xu Ye. The topic of my report today is the effects of freeze-thaw cycles on the erodibility and microstructure of Soda-Saline Loessal in northern China. And I will report from the following four parts. The Soda Plain, located in northeastern China, is distributed in large areas of Soda-Saline Loessal. It's a typical seasonally rainfall region and one of the areas most seriously affected by water loss and soil erosion in China. Freeze-thaw effects on soil structure and mechanical property are becoming more frequent and intense with global warming, which further affects soil erosion in cold regions. Repeat fault-heavy and soil sediments can change physical properties. It's likely to be an effective material source for other erosion chemicals in exacerbating soil erosion. Soil shear strength and disintegration velocity are important indicators of soil erosion. Soil shear strength is closely related to rainfall erosion, rainwash erosion, and interior erosion. The soil disintegration velocity indicates water resistance. So we conducted the freeze-thaw cycles on soil with different water and salt content to obtain their mechanical property and water physical property, and investigate the effect of freeze-thaw action on soil erodibility. Next, experimental program. The specimen preparation and test procedure are shown in the figure on the left. Firstly, the sample was detailed to control the soluble salt content of the soil sample. Then a square specimen was prepared. The basic property of the specimen preparation are shown in Table 1. When one or several freeze-thaw cycles were completed, test, direct shear test, and scanning electronical mechanism test. Part 3, result and discussion. Figure illustrates the relationship between the soil shear strength and the freeze-thaw cycle. The results show that there was a cumulative effect of freeze-thaw cycles on the deterioration of soil strength. The shear strength was more significantly influenced by the water content than by the salt content. The cohesion decreased with an increase in the number of freeze-thaw cycles and reached a relative stable state after 10 freeze-thaw cycles, while the internal friction angle was less affected by the action of freeze-thaw cycles. This result was due to the increase in water content and the seeking of the water film bond between the particles. In the disintegration, all cell samples were completely disintegrated. The disintegration amount was at high 20 to 40% with a few seconds after soil sample were immersed in water, become the edge effect. The increase in soluble salt content and initial water content reduced the soil disintegration resistance. The disintegration velocity of the soil increased during the first 6 to 10 freeze-thaw cycles. The following figure illustrates the typical disintegration curve. The disintegration process showed a 3-stage pattern of fast, slow, fast over time. The disintegration of saline loess soil is related to the pore and fissure structure of soil. The disintegration caused by gas fracturing is the main reason for the repeated disintegration of the specimen in the early stage. Soil disintegration is also related to the interparticle cementation, which is the main cause of the stable disintegration in the last stage. Particle morphy, pore characteristics, character patterns, and cementation are important factors in the study of soil microstructures. Together, they determine the physical and mechanical properties of soil. With an increase in the number of freeze-thaw cycles, the skeletal properties of the specimen are more volatile and broken. The large pores gradually transformed into small pores. The pores were classified into 4 categories according to their diameter. The data show that alternating freeze-thaw action could directly lead to an increase in the total pore areas. This result indicates the freeze-thaw cycle mainly causes the growth of micropores and the conversion to small pores and macropores. Meanwhile, the average pore diameter decreased as the number of freeze-thaw cycles increased, and the degree of pore homogenization increased. We also explored the variation pattern of parameters describing pore morphology characteristics during freeze-thaw cycles, including circularity, convexity, elongation, and fractal dimension. We found that the Soda-Saline loess soil had a relatively small proportion of rounded pores. The pores were mostly long and narrow, and the pore surface smooth. However, they are less affected by the freeze-thaw action. The fractal dimension decreased with the increasing freeze-thaw cycle, which indicates the complexity of the pore structure was lower. The effect of freeze-thaw action on the mechanical properties of Soda-Saline loess soil was mainly driven by salt expansion and the transformation of pore water freezing to ice. This process contribute to the rearrangement of soil structure units and the pore evolution, which affect the association between soil particles, and the soil erosion resistance is reduced. It's highly susceptible to external erosion by wind, water, and other forces. The Pearson correlation analysis shows that the properties of the soil are important internal factor in determining its erodibility. The effect of freeze-thaw action on soil erodibility is an external factor that cannot be ignored. Therefore, to reduce the soil erosion problem of Soda-Saline loess soil, it's advisable to take appropriate measures, such as setting a temperature insulating bed layer to reduce the number of freeze-thaw cycles of the topsoil, reinforcing the soil to increase the shear strength, and slowing down the development of stabilization. Part 4, conclusion. 10 freeze-thaw cycles may be the threshold value of freeze-thaw action that affect the soil shear strength. The disintegration velocity of the symbol will positively correlated with the number of freeze-thaw cycles. The alternating freeze-thaw action results in a significant increase in the number of pores and a decrease in the average pore size. Initial moisture content was the basic factor affecting soil erodibility, and soluble solid content mainly affected the soil disintegration characteristics. About it all I have reported. Thank you, Epler and scholars.